Okay, first thing off, Happy New Year to everybody.
Happy New Year.
Happy New Year. I'd like to do just a quick reminder, if you could please silence your electronic devices as a courtesy to our speaker, fellow members, and guests. That'd be great. Thank you. So tonight's...
You're not done yet.
Tonight's topic title is Lucy's Tour of the Trojan Asteroids by fellow member Bill Higgins. The two swarms of frigid Trojan asteroids circling the sun at the same distance as Jupiter has never been visited by a spacecraft. NASA's Lucy mission plans to change that. Launched in 2021, Lucy's intricate trajectory will eventually fly by 11 asteroids, including 8 Trojans of varying size and composition far beyond the main asteroid belt. Some are leading, far ahead of Jupiter in its travels, some are trailing far behind. Their particular orbits suggest they evolved differently from other asteroids. The Trojans may be a new kind of witness to the history of our solar system. Passing through the asteroid belt on her way to the distant realm of the Trojans, Lucy's first flyby occurred in November. Images of this tiny Higgins surprised the Lucy team, and if all goes well, the best is yet to come. Bill Higgins frequently speaks about spaceflight and astronomy. He works as a radiation safety physicist at Fermilab. He is pleased to have been an NAA member since 1989. He volunteers in NASA's Solar System Ambassador Outreach Program and was recently Science Guest of Honor at WindyCon 48, a science fiction convention. Everybody welcome Bill Higgins.
Thank you, Kurt. Happy New Year, everybody. I'm very pleased to be celebrating an anniversary because last night was an anniversary of January 1st, 1801. And you may remember that on that night, Giuseppe Piazzi was working and he found a new planet. Which was eventually called Ceres. And so January 1st is the anniversary of the beginning of asteroid exploration. Furthermore, I have a great privilege tonight. I gave a couple of talks last year, which was the year that we celebrated the 50th anniversary of this organization. But this is the beginning of the 51st year, right? I am the first speaker of the next 50 years. So I am humbled to be awarded this honor. I have already talked about missions that flew to asteroids, but NASA keeps sending them, and so does the European Space Agency and so forth. So I'm going to keep talking about them until everyone's tired of me. This is about Lucy, which has a spectacular ambition of visiting a whole lot of asteroids, most of them in the famous Trojan groups that orbit the sun at Jupiter's distance, but none of them is particularly near Jupiter. We'll get into that, right? And as Kurt said, I volunteer in NASA's Solar System Ambassadors program, so I agree to do some things or other to reach out to the public and inform them about spaceflight, astronomy, NASA missions, and so forth. And NASA agrees to give volunteers briefings and material and slides and such. So if you see different formats for some of my slides, probably because I lifted them from the presentations of different scientists. And I'd like to thank Dr. Hal Levinson, who's the principal investigator for the Lucy mission, and also Simone Marquis, who is the deputy principal investigator, and they've both given us some presentations, and of course Kay Ferrari, who for many years has been managing the Solar System Ambassadors at JPL. just to give a little context, this is a slide I've shown before, but we're in kind of a golden age of asteroid space missions. And tonight we're talking about Lucy, which is in space and is headed for multiple targets. Psyche has launched, and she is on her way to a main belt asteroid that's metal, maybe, or apparently metal. The Americans collided DART with an asteroid to see if they could move it. OSIRIS-REx has finally arrived at home, or its return capsule has, with an excellent supply of gravel from the asteroid Bennu, and it was preceded by Hayabusa 2. So the collaborators on the Japanese Hayabusa 2 mission have been doing a lot of tests on their own asteroid sample already for a while. The Europeans are launching Hera, I guess, this year. So it's in the last stages of preparation to go back to DART's target and see what happened at Dimorphos, and the Chinese also have a mission that they're planning, and which I've heard might launch next year. But tonight I'm talking about Lucy. Lucy is named for a fossil. Well, it's not really. Let's say Lucy is named for a person. We don't know her name. So she's been called Lucy, and she lived a very long time ago in Ethiopia, and she's a kind of among the very earliest human remains that have been found. So we have her bones. She was discovered in 1974, and the spacecraft engineers and scientists who put this mission together decided that she was going to be their inspiration, and there's a lot of references to Lucy, as we'll see in the names of things and so forth. Now, you may be familiar with the Trojan asteroids. They're once people started gathering asteroids and learning more and more about where asteroids were and what their orbits were, it turns out that although most of the asteroids we know of exist in the main asteroid belt, there are other populations, right? There are some that come near the Earth occasionally. There are some that way out in the Kuiper belt, sort of Neptune-ish and beyond. And these particular groups we're interested in tonight are orbiting the sun at the distance of Jupiter. So each one is in a approximately circular orbit, and it goes around the sun about as often as Jupiter does. But they are trapped in or maybe it's cozy and comfortable, they're not trapped, but they're in the Lagrange points. So then two of the stable Lagrange points that would have been good to put Lagrange's first name on this slide, right? What was Lagrange's first name? Okay. And we'll look it up later. In the decades after Isaac Newton published his mechanics and explained how he thought gravity worked, mathematicians explored all the implications of this. So there's a string of French and English and German names attached to various discoveries, and Lagrange gets the Lagrange points because he found that if there's a body and it's being orbited by a smaller body, and the mass of the smaller body is less than 1/80th of the mass of the big body, then another much smaller body that we imagine putting into space, into orbit with these things, can find some stable points. The tiny test thing you're thinking of about like an asteroid or a spacecraft, if it happened to be 60 degrees ahead of the second body in its orbit, it would stay there. It might go a little further away from the central body. It might go a It'll come a little closer. It might go a little ahead, a little behind, but it would be in it would be in a stable orbit with small oscillations. And that's a nice place where if a thing dynamically gets there, it's likely to stay there. Here's a nice way to visualize them. In this picture, the sun is at the center. The familiar inner planets are here. Earth is blue and Mars is red, right? And much further away from the sun than Mars, we have majestic Jupiter, this orange dot, circling around at 5 astronomical units, 500 million miles away from the sun. And these much tinier asteroids like it where they are, and they have spent a long time in those stable points in orbits where, as you can see, they never really get very close to Jupiter, even though we say they're in Jupiter's orbit. They're about as far, on average, each one is about as far from Jupiter as Jupiter is from the sun. Is there anything on this slide that I should be saying? Yeah. They're all together, and they're kind of neighbors because they kind of swarm together, but they are not a homogeneous population. Study of them, get their spectra, get their colors through a telescope, get their light curves, and you can see there's a mixture of different colors and suggesting different chemical natures for their surfaces. Or maybe different origins for these things, but they all wound up to becoming neighbors. This diversity is saying something important about planet formation. And if we took a good close look at a few of them, maybe we would understand a lot more about, not just about these bodies and the nature of each one, but something about how it got there, and something about the connections between neighbors or objects that have similar orbits to the one that you just studied up close. To simplify something I'm not terribly familiar with, as the solar system came to form in its early stages, dust accreted and gas flowed and so forth, but dust eventually became larger objects and larger objects. And in fact, there was the solar system was filled with objects that were tens to hundreds of kilometers across, called planetesimals. The big ones started to attract more, and that's we gradually colliding with planetesimals is how we grew ourselves a Jupiter and a Saturn and the smaller planets. Okay, and everybody kind of knows this story, but it's also true that as they were all orbiting the sun, they had complicated dynamic interactions with each other, and when we got some bigger ones that were truly massive, they had a profound effect on the orbits of the smaller ones. And there was a general trend over, a couple, 3 billion years. Sooner or later, your favorite planetesimal would come close enough to one of these guys, especially Jupiter, to either be absorbed, in a collision with the big planet, or more likely, zip by the planet close enough to pick up some speed, and the orbits can get pumped that way, and the last encounter might give your planetesimal escape velocity. And a large number of the planetesimals that we started with are gone. They're off in interstellar space now, and not bound to the sun. But a bunch more we're wandering around the solar system and having our orbits perturbed and so forth. This is, slow if you're running on human timescales, but if you run on the timescale that dynamicists think, dynamical astronomers and such, a million years is nothing, and their computer simulations are doing this all the time when when you look at what they're studying. And, on a tens of millions or hundreds of millions of years time scale, these things are whizzing all over the place, and some of them wind up in an orbit that's kind of near Jupiter's orbit, and they get into the L4 or the L5 Trojan points, the Lagrange's little stable pockets, and they stay there. Fine, okay, that's where the Trojans came from. But one of the things that this means is that the earliest, the Trojan points are a museum of early specimens of planetesimals. And they might have collided with each other over the years, and so we might be looking at small fragments of planetesimals or something. But the population of objects there is turns out to be stable over a very long time, and so these guys and gals might be relics of the earliest times in the solar system in a way, and pristine in a way that you can learn about a different kind of population of things than the population of things that made it into life in the asteroid belt, which we're still studying, of course, or the near-Earth asteroids, which have mostly been perturbed out of the asteroid belt and into the inner solar system. So the Trojans are interesting for that perspective. So this mission has the obvious job of let's look at these kinds of things because we've never visited this kind of thing before, and the other science motivation that they may have played this role or be the survivors of planetary formation, and show us a little bit of history. So Lucy was conceived to go out to the Trojans and visit more than one asteroid, hopefully, picking targets in a diverse, some red ones and some brown ones and some gray ones, to get some diversities in the visit. And the mission was planned. Let's see, this is a cooperation between NASA Goddard Space Center and Johns Hopkins Advanced Physics Laboratory and the Southwest Research Institute and Lockheed Martin, which kind of built the spacecraft, and a couple other organizations I'm probably forgetting. Arizona State University, and they all collaborated to build the spacecraft and launch it to go to 7 Trojan asteroids. Well, if you're flying a mission, you also want to do as much ground-based astronomy as you can on your targets, and it turns out that careful study has, or a fortunate occultation has revealed that Palaemon has a companion. So the 7 Trojan asteroids have now turned into 8. And they figured out that they're passing through the main belt in a complicated orbit, so maybe there's a couple of other main belt asteroids they could visit on the way, and that would be a nice test for the instruments and some practice for the people operating this. And so they threw in two main belt asteroids, one of them that they added onto the list after launch. Then it turns out it wasn't 2, it's 3. So we are let's just say that if your job is flying Psyche, at certain times you're going to be very busy. So here's a slide with the facts about Trojan. Like, what's the nature of these things? They are dark. They generally have low albedos, as we'd say in science land. They have, as I already said, a wide range of types. Their colors are different, and they have the visible and infrared spectrum of C-type asteroids. In many cases, they're not very much brighter in a couple microns in the infrared than they are down here at visible wavelengths like blue, green, and red. So if your spectrum is flat, then and all the colors are contributing equally, we call that gray. But if your spectrum, if your rock has a surface that is dim in the short wavelengths, the blues and the greens, but more reflective in the longer wavelengths, like the reds and the near infrareds out to a couple microns. Then it's got a slanted spectrum, right? And we call that red. Astronomers call that red. It probably looks brown. So P types are kind of brown, and D types are kind of red, and D types have a stronger slope there, and they're real red. So let's if we can, let's put a D type and a P type and a C type on our list to study. Some of these Trojans, some Trojans are known to have satellite companions. And you could tell from occultations and light curves and stuff like that they sometimes have odd shapes. There's a variety of rotation rates and so forth, and their estimated densities are in quite a range. Like some seem to be less dense than water, and some seem to be more like rock, although maybe not the heaviest rocks. That motivates you to, because there's a variety, to look at more than one of these. And what this slide says, what are they going to teach us? And I've already said some of these things, but if these objects are like the planetesimals that were the ancestors of the planets, then maybe we can learn something about the ingredients that made up the giant planets, and maybe we can learn something about the ingredients that made up the Earth, including the volatile chemicals like that gave us the gases and liquid water and other kinds of material on Earth. And how did they form? And did they move around in the early solar system? You can't, by looking at a rock, you can't. It doesn't tell you obviously directly what its movements were, but there's a lot of subtle things that people can figure out to get some kind of handle on what their motions were in the previous 4.5 billion years. For instance, some Trojans are in families. They have orbits. They're independent. They're not all together, circling together exactly, but they may be in different parts of the sky at different times, but tracing their orbits back, or looking carefully at their orbital parameters, suggests that hey, this group has a similar inclination and some other characteristics of the orbit that suggest maybe they were once part of one parent body, or related in some other way. So that is the kind of stuff you might study. Again, when you have a chance to sample or to visit a bunch of these with a flyby. So you build a spacecraft, and what does a spacecraft look like? It's going to be living out at 5 astronomical units, 500 million miles from here. So it's the sunlight is going to be 1/25 the brightness that it is here. And if you want to power your instruments with electricity, you need a lot of electricity. And this pretty much means get some solar panels and really, really big ones in order to give yourself the right kind of power. So there's very impressively large solar panels that are when they deploy, they're supposed to unfold like a flower. And give you 500 watts even when you're at Jupiter's distance from the sun. A major problem, like a disturbing problem for Lucy, was that when the flowers unfolded, one panel worked perfectly well, and the petals of the flower came around and made one big polygon, and at the end, when the unfolding happens, the two ends are supposed to come together and latch and make a click, if you like. And that happened on one of these panels. On the other panel, it didn't open fully. It opened almost all the way and then failed to latch. So that was disturbing, and Lucy's team spent much of 2022 trying to, either test to see if running the unfolding motor, the deployment motor again, would have any effect, or what are the structural consequences of this thing not being the perfect rigid flower they would have liked, and will it still give enough power, and will it hold up if we fire the rocket engines and we need to make burns to go this place or that place in our voyage. But the tests led to a decision that they could proceed with it unlatched, and it would meet its requirements. Look, this is a slide I didn't finish, where I was going to list all the institutions, but instead I did it from memory. But it's a slide that tells you that gives you a very vivid image of how the solar panels go, how big they are, and what they have to do to sort of unfold and come together to make a flower. There we go. So launch was as Lucy set sail in October of 2021, leaving the Earth, and is this one of the animated ones? Yeah, great. Lucy left Earth and and spent a year in orbit around the sun. At the end of that year, just about a year later, it came back to the same spot where it had been launched, and so did the Earth. So it had an Earth flyby. And the Earth is, for our neighborhood, the Earth is a pretty massive body, and if you do the right things, you can get a slingshot boost from an encounter with the Earth's large gravitational field, and this is a famous trick that lots of interplanetary spacecraft have used. Well, Lucy does it quite a bit. So after just a year, Lucy hasn't gotten very far, but but the first encounter has given it enough oomph to put it into an orbit where it takes about 2 years to go around the sun, and it comes back to the Earth again. Now it's considerably further from the sun. It's going real fast down here and not so fast up here, but we've pumped up the orbit to go into the asteroid belt. And it was during this part of the orbit that in 2023, November 1st, 2023, it made an encounter with its first asteroid. However, these slides come from a briefing that was before they added that asteroid to the picture. So we're not going to see it here. We'll get back to it later. Some of the targets are still going around. The little white dots are making their trip through the solar system, as you can see. And the first main belt asteroid that actually shows up in this briefing is called Donald Johanson. It's an asteroid that was named for the archaeologist that discovered the Lucy fossil in 1974. A look at a main belt asteroid. Here's what it might look like. We can't. These things are all little dots in the telescope. But if what it might look like, or if on a scale where this green bar is 50 kilometers. Donald Johanson is a pretty small asteroid. Okay, and Lucy's going around and is now in orbit that will take it all the way out to the distance of Jupiter, and again, nowhere near Jupiter. But after let's see. Launched in 2021, so we've been almost 6 years in space. The spacecraft is finally getting to one of its major targets. And Euripides is a pretty large asteroid. That's I'm not carrying the numbers around here, but you can see on the scale of 50 kilometers, it's bigger than that, and probably not as much as 100 kilometers. It is a C-type, a dark gray asteroid, Lucy doesn't stop. All of these missions are flyby missions. There's just a short period when the asteroid is bigger than a dot in the cameras, and when you can start doing some science, and there's about one day when you get the really good pictures or the really sharp spectra, and then you go along. But this is at this point, Lucy will already have encountered 2 main belt asteroids. Asterisk, I'll talk about that later. But so by Euripides, which is a big target, they ought to be pretty well practiced at doing flybys. Euripides has a companion called Queta, and very soon afterwards, later in 2016, that was an August encounter. We're now in September of 2027, and so it's only been a few weeks, and Lucy is visiting Polymele, which is a what does it say? P-type. It's a reddish, or we'll say brownish, maybe reddish. Object sort of looks like maybe in the 20-some kilometers across. As I said, before launch, they didn't know that Polymele has a companion. So you get two more for that encounter, and not very long after that, while we're in the leading Trojans, the L4 group of Trojan asteroids, it's time to visit Lucas. This is now April of 2028. So there's been a few months of rest and a few months to downlink all the data, and they're not in so much of a hurry. But this is a D-type, very reddish object, and substantially big. Looks to my eye about 30 or 40 kilometers across. And the orbit gets interesting at this point. We have, there's one more, Orus in November of 2028. So now in the summer of 2027 and the fall of 2028 or spring and fall of 2028, we've visited a whole bunch of the L4 leading Trojan type asteroids. And that should be enough for anybody. It's already an ambitious asteroid mission that's visited the most targets that anybody ever has, but its elliptical orbit, of course, is going to take it back to the inner solar system. And in fact, its perihelion is pretty near the orbit of Earth, and guess what? In 2030, just after Christmas, we get another Earth encounter and another opportunity to pick up some speed, or change the direction, or change the inclination a bit, and alter our trajectory and go on. Lucy is still going to be basically on this big red ellipse that it's following, but you could tweak the ellipse a little bit to change the speed and time you're going to arrive at certain places. Well, we take advantage of that kind of encounter, then there's going to be another long climb out of the inner solar system and through the main belt and back to the orbit of Jupiter. But if you choose your orbit correctly, the timing is such that in all the years that have gone by, Jupiter has sailed by and you were nowhere near it because you were down in the inner solar system. But as you come back, you happen to be crossing Jupiter's orbit just about when some of the trailing Trojans are showing up in their path. So you can visit them if you like, and Patroclus and Menetius are a really interesting set of quite fat asteroids, and they're comparable in size. It's not a big one and a little one here. They're twins or anyway siblings, and they're P-types, so they're more reddish or brownish, and they hold some secrets that we don't know yet because we haven't looked at a P-type asteroid close up, and they're dynamically interesting. Oh, doesn't this thing have a little animation of them?
It did, but then it stopped.
Yeah. Okay. Let's play that one again just to watch the movie. Stop it.
There you go.
Oh, there they are. Yeah. Okay, great. Okay, so far so good. I've lost count of how many asteroids we're up to, but here's a list of the major Trojan targets. Euripides and its small companion. That's 2. Polymele and the not in this briefing companion. So that's 4. Lucas and Orus. That's 6. And then a long time goes by, and sometime in the 2030s, we come back to Jupiter's orbit, and we're in the L5, and we get to see 2 more. So that is 8 Trojan asteroids, unless we find between now and the 2030s, telescopes find maybe a couple more companions to these things, and we might rack up our count. But this is and then Lucy will keep on orbiting and just go. I guess maybe that actually is the end of the show in the animation sense. But it'll go be in a red orbit that takes it back to the inner solar system again and again. There might be the next time it comes out to Jupiter, no Trojans to look at, and the mission ends officially when it visits these two guys, the last ones, Patroclus and Menetius, and it's done. Here's a little museum of these things. I added Polyphely's companion. It doesn't officially have a name just yet, and somebody has to think of an appropriate name that fits all the criteria, and then get the approval from the International Astronautical Union and so forth. So while this object doesn't have a name, somebody on the team decided, got some idea that the classical figure of Polymele, a female personage who shows up in Greek mythology, is somehow associated with sheep. So they've named this thing after Shaun the sheep, the Aardman Animations character. Do I need to go to? I have a backup slide. That's appropriate here. Probably this one. Yeah, here's the occultation where Polymele's companion was found. Everybody was setting up their telescopes and watching watching the asteroid cross a star or not cross a star and make a little bit of dimness. You know how occultations go. Maybe not everybody knows how occultations go, and the telescopes keep watching and measuring the brightness of the star as the asteroid has passed it, and people noticed at some later moment that there was another dimming, in fact, along several of these chords, and so there's a thing smaller than Polymele that's the right distance from Polymele, and they, as I said, they decided to name it after Shaun, and that's not going to be the official name, but if you need a cartoon character name to refer to a thing in your mission planning and say, what camera angle we're going to have on Shaun or whatever, it's useful to have a name. So now I have to go back to the slide that I was showing. Yes, I've talked about the path, the mission, the agenda here, and the targets it'll visit. I want to mention Lucy's instruments. What kind of studies will it be able to make when it gets where it's going. Well, the answer is that it's mostly got instruments that are copies of instruments that have flown on other spacecraft, and you can't have a golden age of asteroid exploration missions unless you have previously had a golden age of small, lightweight instrument development, and with gadgets that take only a little power but give you a lot of data and so forth. So, and the instruments that have been that are copies of previous instruments have been given an L and an apostrophe in front of their names. So if you follow the New Horizons mission, there's a high-resolution camera and a sort of, I forget, a telescope about this aperture, and it was called Lori on New Horizons, but it's La Lori on Lucy. So that'll be a familiar camera. The thermal emission spectrometer from one of the Mars missions, I forget which one, but it's been a workhorse in orbit around Mars. Well, we got another copy there, and it serves basically as a thermometer and an infrared spectral instrument. Also, a really nice imaging spectrometer is familiar from New Horizons was Ralph. Ralph, the inner guts of Ralph have both basically an imager, a color camera, not as high resolution as Lori, but pretty good, and also a light path that where what's coming into Ralph could be shunted into a spectrometer that handles visible and long wavelength or short wavelength infrared. So it's very good. It's the instrument you want for composition. And let's see. There's a couple of specialized cameras that are useful for navigation. This is going to be very far from home, and we can't have people steering in the last day or two before before the moment of closest approach. We can't have somebody in a control room with a joystick sending signals to this thing. There has to be the right hardware, nice cameras, not cameras that, maybe you don't need cameras that do all the science that Lori can do, but you need good cameras that can feed images to your optical navigation software, and it's basically kind of a missile that's homing in on a target. So it needs to tell the spacecraft propulsion how to make the last tweaks to go right to the spot, the place and the angle that they want to use for the flyby. And so that's your sort of navigation system. And of course there is a large parabolic antenna attached to this thing that communicate across interplanetary distances. But if you put the right hardware among the radios that this thing is using, as we see so often in spacecraft, it can measure. It can work with ground stations to give Doppler information to tell you very, very precisely the velocity of the spacecraft, and of course the range of the spacecraft, and that kind of data can be turned into not just useful information about the position and velocity of where it's flying, but also some information about the influence of the tiny gravity of an asteroid on the path of the spacecraft. So you might be able to get some information about at least the first couple of coefficients in the asteroid's gravitational field. Orbiters are much better for that sort of thing, but here we are. Okay, wait a minute. Can I stop this one? No, let's go back to this one. The next slide, you've seen the perfectly sensible red elliptical orbit that changes some shape and does clever things that Lucy does. But imagine that we watch this not from the point of view of the sun at the center, but imagine that you're an angel who decides to hover over Jupiter and keep up right above, I don't know, let's say the North Pole of Jupiter in the whole, all the years that the mission are going. Now, if you don't like angels, then I invite you to contemplate a propulsion system for a spacecraft that could hover above Jupiter for, 12 or 15 years. But anyway, your point of view, Jupiter is going to stand still in the following animation, or approximately. It might go a little bit further from the sun and a little bit closer, but it's this kind of salmon-colored dot at the top of the picture. And Jupiter and you, the angel, are watching this spacecraft, and it's going instead. The sensible ellipses that we kind of understood from the from previous animations. Now Lucy has now gone out to Jupiter's orbit, and it's visiting the leading Trojans, and then it's going back towards the sun, and then it's coming out to the trailing Trojans, and that's more or less where the movie ends. I'll play it a few times because it's and here's, I guess Jupiter's this yellow dot at the top, and it's not quite fixed, but it's almost fixed in this picture. And the one of the green, the green path is the main belt asteroid Donald Johansen, and the blue is the Earth, and the spacecraft is just making this squiggly magenta curve that goes all over the place, and it's glorious. Or I hope you agree that it's glorious. Great fun to look at. Now I'm reluctantly going to leave this slide and go on to another one. Oh, because it's time to think about the asteroid that Lucy has already visited. The first one on its list of targets, which was named. It didn't have a name when this mission got started, and it was just a number in the catalogs. So the folks at on the Lucy mission asked if they could name it, and they gave it the name Dinkinesh, which means "you are marvelous" in Amharic, the language of Ethiopia. But it's the Ethiopian name that's given to Lucy, whose fossil remains we have studied. Like I said, this asteroid was known, but it wasn't considered to be a target because it might be too small, and it was after launch, that a year or so after launch, that NASA announced that this is going to be added to the list. Because if we tweak the orbit just a little bit, we could come within 400 kilometers of Dinkinesh. So, what would you like to know about an asteroid? Well, how far away is it from the sun? Somewhere between 2 and 2.4 AU, or think of it as a couple 100 million kilometers, and it's got a somewhat eccentric orbit, and I didn't write down the inclination, but it's a couple degrees or something, and it goes around the sun in this not too far from circular orbit every 3.25 years. So the game is to get this is for Lucy along the way after its first Earth flyby, after it launched its first Earth flyby here, to keep going and pass Dinkinesh out beyond the orbit of Mars, right? This guy does not have an animation, but the next one has an animation. So let's play it. Lucy actually, there are little, you're going to see some of the images that the navigation cameras took to watch the little dot that Dinkinesh represents as it moves through the sky, and that helped refine the navigational information. So we're in the middle of September of last year here, taking these pictures and refining position information. And Lucy kind of goes beyond from beyond Higgins in respect to the sun, but they're going to come together on November 1st and have an encounter. And so this is a slide that's kind of showing you how they acquired early information on Higgins' trajectory. And when they downlinked the first images on November 1st, November 2nd, the spacecraft was able to gather a lot of information, but it took a while to play it back, right? So the pictures that they chose to send down in the mission planning showed to everybody's surprise that, well, I guess maybe there might have been a hint earlier in ground-based astronomy, but Higgins definitely has a companion. So it's time to think of another asteroid name, right? Here's a little animation that shows Higgins, which is about less than a kilometer. It's about, it's close to 800 meters across. And its companion is much smaller, like 100 meters or so. Well, as time went by, more data were downlinked, and about a week after these pictures were released, maybe like the middle of November, pictures that were released that showed, wait a minute, it's not 2 rocks, it's 3 rocks. We still have Higgins, and we still have a small companion, but the small companion looks like 2 distinct asteroids. Actually, they're a contact binary. Two rocks that possibly they orbited each other for some years or something, but anyway, they've settled down to be, they touch now. They're counted as one object. So, but even, so we at least got picked up one asteroid more than we were counting. That Lucy's score is up to 2 now, and there are still like 9 to go that we know of. I think it was Hal Levinson who commented in some press conference that Lucy's list of target has now turned up to 11, which is funny if you're a fan of Spinal Tap, and puzzling if you're not. Here's a slide that shows sort of why it looked like there was one companion, and then later it looked like there were 2 companions. The first encounter, or as the encounter went by, the spacecraft was looking from this angle down at Higgins and its satellite, and the satellite was behind Higgins, but not obscured by it. It was, so you could see there were two objects, but the spacecraft turned, and the camera platform also turned to try to keep looking back at this system and taking more images. And picture B was taken from the angle that you see after Lucy had passed the satellite, or had passed Higgins, and you could get a better view of the separation between them, and apparently we were looking at the double asteroid head on, where there's another one behind this, but they count as only a single asteroid. The name that's been assigned to this companion is Selam, which means peace in Amharic. And Dinganesh, as I said, is a name of the fossil and means you are marvelous. We're really, this is probably not the last times that people will be harking back to the to ideas that surround Lucy and her remains and the people who discovered them and so forth. But here's Ralph can do color images, so this is a color image. not as high resolution as the black and white image we got, but this is a terrible slide that you should not show to an audience. I got it in a briefing, but I can show it to you because you have seen the frame, the point of view rotating with Jupiter, and you understand these squiggles are now not unfamiliar for you, even though they never stop looking weird. But this diagram shows you kind of where in this geometry the various encounters happened relative to Jupiter and the Sun. So this is Dinkinesh, the one we just had, and the Amharic name of is actually spelled out here, which is nice. And I kept this slide in because it has the timetable. There's another Earth gravity assist at the end of this year, December, and then next year in springtime, April 20th, there'll be an encounter with Donald Johanson, which is here in the middle, sort of in the asteroid belt somewhere. And then it will take a couple of years to get out to the Trojans, and the first Trojan encounter is Euripides and its companion Kata, August of 2027, followed quickly in September of 2027 with Polymele and its satellite, and then also in April of 28, Lucas, and in November of 28, Horus. So 27 and 28 will be an intriguing year for people who are curious about Trojans and will have collected a lot of information. Then it takes years to go back into the inner solar system, have a Christmas, or almost a couple days after Christmas, encounter with the Earth. EGA is Earth Gravity Assist, pick up a little more speed from the gravity, and take 3 more years to gradually cruise out to the trailing Trojans at L5, and encounter Patroclus and Menetius and whatever else they may find out there. And then the mission will have reached all of its goals 12 years after launch or so, and that's the Lucy mission. Do I have? Oh yeah, and this is the final slide, because the principal investigator could not resist putting this in, and really I couldn't resist either, keeping it. So if you want to learn more about the mission, then there are many ways that NASA gets information to you. NASA has a Lucy site. Southwest Research Institute has one that's probably got more technical. And connects you more with the science, but it's on Twitter, it's on Facebook, it's on Instagram. It will be on social media that haven't been invented yet by the time it gets to its first Trojan. And that's my story. Any questions?
I have a question.
Yeah.
A lot of these Trojan asteroids are very irregular in shape, and I was wondering, their companions, are they due to an acquisition or due to the Yorp effect?
Oh, the Yorp effect, one of the subtle forces that affect the trajectories of asteroids, but
Right, they'll cause a differential torque in the asteroid. They can maybe split those pieces off.
oh, it's probably not big enough to split pieces off.
Okay.
No, I mean, I don't have a good idea. I don't have good knowledge of how a little asteroid might come to orbit a big asteroid. But it could be the only survivor of an impact that sent things flying into the void. It could have wandered in. There are lots of objects circling the sun out here, and they've each got their own independent orbits, but they stick close to the L4 point or the L5 point. So an object could, through various perturbations, maybe Saturn went by a few years ago and changed its orbit a little bit, or maybe the Yorp effect or other effects could change its orbit just enough that when it comes near to, let's say, Pleiades or Eurybates, then it just happens to have orbital parameters around the sun that are slow enough with respect to the big asteroid that it gets captured. But I'm not really an expert on this kind of stuff, so I'm just making up a story to tell you now.
Thank you.
Yeah.
Bill, not on Lucy, but on, I think it's Benau. How's NASA doing with getting the container open? I mean, is it fully open now?
Okay, in Houston, in what I think of as the Moon Rock Lab, the people are working in their clean rooms and glove boxes on this precious container you're talking about that was part of, that was collected by the OSIRIS-REx spacecraft, and now they have their rocks, but they're having difficulty getting the lid open, as you say. Last I heard, they were they're taking the time to make special tools and work out special procedures that might work. Things that come in contact with these samples have to be made of some materials that are only on a short list of materials. There's an interesting video by Brother Bob Mackey of the Vatican Observatory, who's a collaborator on all of this, and they needed a gadget to measure density of a sort that Brother Bob has worked with, and he realized that in his makerspace lab with 3D printers and he's good at making stuff, that he could make an instrument, a pycnometer, out of like the right list of approved materials, cheaper with Jesuit labor, I guess, than anybody else who had bid on this, and so he built the instrument that they're able to use in the environment that they're keeping the rocks in. And he's got a YouTube video about the building the instrument, so it's worth a look. MACKE, Bob Mackey.
It's not open yet.
It's not open yet. They are fabricating some new tools, so they're planning to try some stuff. But the last I heard, they're taking their time, and it hasn't been open yet, unless it has in the last week or two.
Bill, I think what I heard most recently was they've got it on schedule for like March to open it up because they're not hurrying about it. They're making a new tool. They're doing other stuff. They're just like, don't rush us. But I think they're thinking it's going to be like March before they pull that bolt out that's stuck on it. Yeah,
it's don't force it.
Well, they got a ton of stuff off of it already that they're playing with.
That's true.
Yeah.
There was a lot of loose material
Yeah.
outside the inner container, so they've got people in the labs with their microscopes and instruments have a good number of grams to play with while they're waiting for the main stuff.
I just thought it was an interesting sort of point of this project here that they can't get the lid off.
Yeah,
I don't
it
think
is.
that was anticipated.
Right. I'm on the one hand, I'm laughing with everybody else who's laughing, but on the other hand, I can put myself in the shoes of people who have a laboratory and have a precious payload that they waited years for in their lab, and it's
We can miss something.
right. So I'm not laughing too hard at that. Yeah.
Bill, can you give us a sense of just how close these asteroids actually are to each other? Are they like the distance from the Earth to the Moon, or are they closer, are they further?
Like for the ones that have companions.
Well, I mean, just like the ones in the L4 and L5, the Trojans themselves, how dispersed are they? Can you give us kind of a sense of?
When we watched the animation, we saw green dots traversing a sort of, football-shaped cloud. right? They were in a zone. They all circled the sun, and Jupiter circles the sun, and they're all in a zone, and they're moving through that zone, and it was kind of like a blob, an ellipse, right? They never get too far away from the L4 point, but well, that scale is like, it's a fraction of the way around Jupiter's orbit, right? A few degrees, I suppose, that these things stay inside of. But Jupiter's orbit is 500 AU, so it's sort of 500. Yeah, it's 5 AU. So it's sort of 15 AU in circumference. So a few degrees on that is millions and millions of miles wide. So even though there are a lot of Trojans, that probably on some slide I said how many, or more than a kilometer, but I forgot to mention it. But there's still, like, there's an enormous amount of elbow room. So if you and I were to go visit there, we would maybe stand on one of these Trojan asteroids, and we would look around, and there would be pretty much no other Trojan asteroids visible to the naked eye. But you might pick them up in binoculars, or there might be a couple, but like, of the tens of thousands of big ones that are there, yeah, there's still plenty of room between them. However, if instead of a person who puts on a spacesuit and walks around asteroids, you're a dynamics person, and you think about this in million-year timescales, then yeah, that cloud, which has all of these things moving and interacting, there's going to be collisions, and they just, at least occasionally, even though they are rare on human timescales, but on geological or astronomical timescales, there might be a lot of them. So they haven't. We can say that since the beginning of the solar system, they haven't undergone enough collisions to grind the entire Trojan point in cloud into dust. But there must have been a number of collisions, and we can actually prove, for ones that have similar orbits, sometimes you could trace them back to more or less the collision orbit or the orbit they started in. Yeah.
The astronaut Mike Massimino, if I'm pronouncing his name correctly, was once asked what he thought of one of the Star Wars movies with Han Solo flying through the asteroids, and he said, well, Hollywood has taken a few liberties with that. The average distance between asteroids in the main asteroid belt is 100,000 miles between the asteroids. Now, I don't know if that can be applied to the Trojans, but there's a lot of space out there.
It might be the right order of magnitude, or it might be the average distance between Trojans might be somewhat smaller, because the volume that they're in is a lot smaller than the donut of the main belt. But that's, yeah, thank you for informing us of that.
So are all of the Trojans from beyond Jupiter's orbit, and it wouldn't be, the orbital dynamics prevent main belt asteroids from being ejected and captured into the Trojan belt?
I do not know enough to answer that question. Maybe we could go find somebody who specializes in that stuff and have them give a talk. Yeah.
So as a class, are the Trojans considered to be somewhat different physically from the main belt asteroids, or are they more or less a lot the same except for their location?
People tend to speak of this kind of thing in terms of averages, but on average, they're a lot like. Oh, sorry. There's some. The gray ones are a lot like the main belt populations, and the red ones are rarer in the main belt, and also all of this stuff may have formed in a colder place than the asteroid belt typically is now. So they might be more icy. But so they're not so distinct that I could give you one of these rocks and could say, oh, that is from the asteroid belt this one is from the Trojans. But you could perhaps use your vast knowledge of asteroid and meteor science to say, I give you a 40% chance this is from a Trojan. And we'll probably be able to answer questions like that a lot better after this mission is completed.
One more question. What's Lucy's design like?
It's always expressed in nominal terms. So the year 2033 is when it visits its last asteroid, and it's supposed to last long enough to downlink all the data from that. So, perhaps summer of 33 is what it's designed for. But, build a spacecraft without making very sturdy and have lots of redundancy and plans for if this fails, we'll still be able to use this and that kind of stuff, as you know. So Lucy
They didn't
could
design
go.
it like your car, in other words, to die at a certain time.
Yeah, it's not. And it also might be partially working even if something breaks, right? But it looks to me like there's a lot of empty space that over the years beyond 2033 where it's not going to have, not going to be going anywhere near a target. I don't know, passes through the main belt, so maybe there will be some more candidate main belt asteroids that it could possibly go near or something. But the future, unless Lucy lasts a very long time, like I would guess, and this is just a guess from me, not from NASA. I would guess more if it's still running more than a decade beyond the last Trojan encounter. Maybe they could use it, maybe even some Earth flybys, but it will still have any propellant left to do this. Maybe it could be maneuvered into visiting the L4 Trojans again. It's going to be in an ellipse. It's approximately the right orbital parameters to keep going to Jupiter. But but how many cycles? We could doodle. Let's doodle this over beer after the after the meeting. Yeah.
So Bill, you talked a little bit about one of those solar panels didn't fully lock in at the beginning. Are they getting their full 500 watts out of this thing?
Yeah, or pretty close.
Pretty close to it. So.
Yeah, very, very close. At this time, it's much closer to the sun than it will ever be again. Or not ever. I guess it does, but it's fairly close to the sun compared to where it's designed to operate. So it probably has fairly generous power available right now. But you want it to have adequate power for the flybys out there. Is there another hand over here? Maybe not. Any further questions?